All right. So welcome everybody. We start a little bit earlier today, and the session won't be as long as in the program because I have to get my train back to Germany, and the only chance is to get it at 3 p.m. And they told me I have to be there 45 minutes before the train left. So I hope to make it 20 minutes before it left. So sorry for that. The session is about Java on wearables, but it's a lot about hardware. And because I built something, it's this little thing. But let's start. First of all, because I'm working for Oracle, I have to show you this slide. And I give you some time to read it, and I think you read it already. So my name is Gerrit Grunwald. I'm working for Oracle as a developer evangelist. And this session is about wearables. Who has a wearable in the room? Something like a smartwatch or something like that? Okay. So these are some examples. You have earphones, not available yet. They will come in September, hopefully. Then Google Glass, smartwatches, clothing, insoles. Very interesting things. And there are many, many more of these things. And the use cases for these wearables are usually something very popular, fitness and health tracking, right? So this is, who uses something like that for fitness and health tracking? Most of the people, right? Runners and all that. And then if we use something like that, we talk about data producing wearables, because this stuff normally just collects data from your body or from something else and then just publish the data somewhere. Then also very popular is location tracking or distance, like GPS navigation, which is in this case data producing and data consuming. So it does both. And the last one is informational. That means, for example, augmented reality. So you see that I also use a mobile phone as a wearable, because in principle it's really not a big difference between a watch and a phone. So technically I agree it's a difference, but for the use cases you can use both things as a wearable. For example, my phone collects all the steps that I walk when I have it in my pocket, so the watch does the same. So this is the reason for that. If we take a look at the current situation, then it's like this. We have lots of devices, right? This is not only this Apple Watch and Android Gear stuff, but it's all these fitness trackers and many more companies coming up with GPS trackers for kids, for pets, for elderly people, for whatever, for cars. You can put stuff in your car that tracks your driving style and all that things. All these devices come with predefined features. That means I have an Android Gear. Then I buy an Apple Watch, because the Android Gear doesn't have heartbeat or heart rate counting, but the Apple Watch has. Oh, that's great. So Apple Watch on the right, Android Gear on the left. Then I need something else. Blood pressure. Oh, I put something here. So we end up with all these devices, right? That's not really good. There is no real standard for all these things. And the other problem is you can't really combine it. So I can't, and I know there's a big problem at the moment for Google, for example, to access an Apple on an iPhone, access an Android Gear watch. It's not allowed by Apple, which doesn't make it easier. And this is really the biggest problem, because you are bound to the vendor, either to Google or to Apple or to some other vendor. So this is really the biggest problem of all. But what if you need something special, right? The only solution is you have to do it yourself. And that's exactly leads me to the point. The idea was born in 2013, and it's the so-called JRunner project. And I started working with that thing, this is the current state. It looks a little bit ugly, but we will come to that later. I had two friends, and one of these guys is an ultra-marathon runner. So, and he told me in 2013, I have to always say that it's a little bit time between that. He told me, well, it would be so great if I can run and someone can monitor me live somewhere, wherever. For example, I'm running in the States and he's sitting in Sweden. And then we discussed that problem with lots of beer, which was very funny. And in the end, yeah, that's it, let's do it. Next morning, breakfast. It was not that good anymore. Everybody had like this with a big headache, and then I was the only one who said, okay, I think I can do it. So I had some ideas for features. First of all, of course, we would like to track the location of the person. That means we need some GPS device, whatever it is. But some GPS device is needed to add on this wearable. And we would like to get latitude, longitude, altitude, speed and heading, if possible. Depends. Heart rate for running or for every kind of professional sports, heart rate is the one factor that you have to monitor. So we need something like heart rate monitoring. Then I had, like I said, this is the current version, and I went through, I don't know, 10 or more different things with display, without display, with buttons, without buttons, with everything, with external sensors and internal. And so I thought if we have something that doesn't have a display, we need some kind of feedback. I need to know if the battery is running down. Then usually if you have some kind of a lithium polymer battery, you have to switch it off, not when it goes down to 0, but maybe at 10-15% to really make sure that the battery will be alive the next time you charge it. And for that kind of reason, I needed something like vibrational feedback in this device. Then that was a little bit special, because in the meantime, I agree, you see, I wear, this is not an Apple Watch, that's an Android Gear, but or Google Gear. So this is something you can't do. My device can do text-to-speech. That means I can send a message via text, and this thing will read it to me, to the runner. And that was one of the ideas, that you can somehow interact with the runner, at least in one way. Then something very simple, a switch to switch it on. So it sounds so simple, and it's not. So is someone working with a Raspberry Pi? Who has a Raspberry Pi? Who works with a Raspberry Pi? Okay, always the same. Same goes for Arduino, it doesn't matter. It's just, people have that, yeah, I have this Raspberry Pi. Yeah, if you ask them months later, yeah, it's still on my desk, I didn't find the time, but it's so great, yeah, someday I will do it, okay. So if you start with the Raspberry Pi, you will figure out it's not easy to switch it on and switch it off easily. If you switch it off like pulling the plug, then congratulations, the SD card is gone. And so this is all these things, if you don't think about it, you will stumble upon that problems. Then also very important is monitoring the battery. Sounds easy, is not. Right? You need some electronics to do that, or some mechanism to make sure that you always know, is the battery charged or not. Right? For you, it's normal to look at the phone and say, 25%, put it in the charger. But if you have something like this, okay, no idea. So what's the battery? So we need some mechanism to monitor it. And because I have no display, the idea was remote control the device with my phone, right? Or with a smartwatch, doesn't matter, with something that has a display. So this is ideas, and now I will get through the points and you will see how far I got. So the whole thing is running on that little friend here. Does someone know that thing? This is an awesome device. In principle, this is a Raspberry Pi on steroids, because it's hardware compatible, and the W is for wearable, and it has some additional features, like it has a charger for lithium polymer batteries, and it has a real-time clock on board, and it has a connector for a real-time clock battery, and it has also a 12-bit analog digital converter. Problem with this device is that Hardkernel bought the first batch from Broadcom, the chips for the prototyping, and they did the prototype, and when they start selling it and ordered the second batch of that, then Broadcom said, sorry, it's just for one prototype. So they don't get it anymore, and you can't buy it anymore. So only the stuff that is from the first batch is available on the internet, but there won't be a second one. That's really a mess. The nice thing is this is nearly half the size of the Raspberry Pi, and it comes like this. So no headers are soldered. So the only thing that you need, you can solder everything you need. Like here, usually is the USB port. If you don't need it, you don't have to solder it on the board, which makes it really small. And this thing fits completely in this device with battery, with all the sensors. So, and I'm using Java SE8 embedded on that. because it's like in principle, this is a desktop computer, right? Raspberry Pi is nothing else like a small desktop computer. So that means this is for an embedded device, for a wearable device, this is quite powerful. And there I can run Java SE embedded easily. Even Java ME embedded would be possible, but hey, if I can use SE, I have lambdas and all that stuff, why not? And then there's something like Pi4j. Does someone know Pi4j? If you go with a Raspberry Pi and with Java and you would like to do some hardware stuff, then this is the library you have to use. This is a wrapper around the wiring Pi library, which is a C library. And this is the really best Java library then when it comes to hardware connection that I know. It's really very convenient to use. And you can find it on that link. So now let's take a look at the sensors. We start with tracking location. GPS, right? Sounds easy. It's not. These are all the GPS modules that I tested. And when I say test, then it means for each of that modules, I have to create the whole electronic setup and case and all that thing. So that really takes a lot of time to build that stuff. To put it together with some wires is easy. It takes a couple of minutes. To make it small and reliable in a case, that's the hard part. So I started with this one, very nice. Then to that one, it's faster and smaller, but consumes too much power. So then I went to this with an external battery, with an external antenna. So you had the antenna somewhere outside, which is not very convenient if you have a wire somewhere. Then I saw this guy, which has a really good GPS engine from uBlocks. And I thought this is the right thing. And yeah, now I ended up with the last one. It's this. From CSG shop. CSG shop is the URL. And they have really nice GPS receivers. So if you try planning to build something like that, then use one of those. They are not cheap. 100 euros for one of those. But it has really one of the best GPS engines on the market at the moment, which is the uBlocks M8 engine. And I thought the engine alone would be, that's the really the factor that makes the difference. But I learned that it's not the GPS engine alone, but it's also the antenna. And to give you a little idea, I hope one can see it. This was the HAB supplies. It's also based on the uBlocks engine. And here you see I recorded the track, and this is some kind of a river. And I just ran along the river, and you see what happened. It's really... And the interval is 5 seconds. So every 5 seconds I measure. So it's really the exact same route. I really just exchanged the chip, and then it looked like this. Same engine, just a different antenna. And to be honest, this antenna, the helical antenna, should be better for wearables, right? That's usually, they say, okay, this is better because it works better when it's close to the human body. But this little guy, which is, you can maybe see it here, that's the antenna. This is so sensitive that that works just great. It's perfect. It's better than my phone sometimes, so really good. But like I said, it's not cheap, so 100 euros. Okay, and you get something like this. It's NMEA, National Marine Electronics Association. They created a protocol, and this is the stuff that these GPS receivers spit out on the serial port. And usually it's an interval of 1 second. So you get these strings, you just have to parse it, and you get the data out of it. They have different sentences. So this is just a small list. It's a huge list of different things that you can find of sentences. And we only need the GGA and VTG. And that's the two sentences that I use. And usually a GGA sentence looks like this. And you can see here the time. It's 12 o'clock. It's 12:30. Then we have latitude, longitude, north, south, and east, west. Fixed quality. Then we have something like HDOP, which means horizontal displacement of position. And this is a factor. And the problem is to really, your phone. And if you walk with the phone and use the GPS and you start the first time, then you see a blue circle around the point, and then it gets smaller, right? This is the accuracy. And this is really dependent on the GPS engine. So the U-Blocks engine, for example, they guarantee that it should be as good as 2 meters, maybe a little bit below 2 meters, so that you can't get better than this. And you have to multiply this with this 2 meters. And you have to know this 2 meters. So some people just use this factor, and this is not right. And if you have a really cheap GPS receiver, then the accuracy of the engine itself might be 5 meters. So you end up with a really not precise location. So we have altitude and the unit, and then mean sea level. And again, the unit. So this is something you have to pass, and I've wrote a little Java library that you can find here that does, you just have to put in the string, that's all. And then it gets out the data, so you can use it for, I think, it's not only for GPS, because this is for GNSS, which means Global Navigation Satellite System. There's not only GPS, there's GLONASS in Russia. Then we have Beidou in China. And there will be, hopefully, someday Galileo in Europe. So, and this receiver can handle up to 2 systems at the same time. So you get much better precision with this. So the next thing was tracking heart rate. And I tested these different devices. And I started with this one. Yeah, that looks funny, and it is, because you put it on your finger. And you have the wire up to the wearable, wherever you have it. And you can imagine that if you would like to start running, and you have to tape the wire somewhere on your arm, and yeah, you can imagine. It's not really convenient, and also the measurement, it's optical. It's like the Apple Watch does it. It's not that precise. It works, but if you know the polar straps, this stuff is really, that's really great. And luckily, they also give you these little breakout boards. I tried this one, which is great. And this has all the electronics and the analysis of the heart rate inside. So that means it just takes the signal from the strap and gives you just the clean, that's the beat per minute. But it was a little bit too big. So I thought there must be something smaller, and it's this one. It's also from Polar. And this is just the sensor that gives you a 15 millisecond pulse every time your heart beats. So you have to calculate the heartbeat by yourself. Sounds easy. Problem is that the sensor is not really, how should I say it, reliable. So that means sometimes your heartbeat is 250 or 300. Sometimes it's 20. You can imagine that doesn't really work. So you have to do some filtering and stuff like that on averaging. So it's really small, it's cheap. And I tried that. And this is the code that I need to really access it. This is just a short example. So to show you the Pi4J stuff, which is really great. So you just get the GPIO controller once. Then you define a GPIO pin digital input, because this is just a digital high or low. And then you say it's a Raspi pin GPIO 04. Unfortunately, this is, of course, not the 04 that is defined by Raspberry Pi. This is the 04 defined by Wiring Pi. And this is different from all others, so that you need some table to really get the right pin. But luckily on the Pi4J page, they have a nice image that shows all the pins. And then you only register a listener to it. Every time the pin is high, the listener will be triggered, and then you can call your method. So I just use here a lambda expression and call the beat method in my heart rate monitor. And here I do the filtering. So if it's larger than this values and lower than that value, so then I just count 10 beats, build the average, and that's the heart rate. I compared that to a professional device, and I was always like 3 beats off, so it's not that bad. So for me, that was more than enough. So because I'm really not the sportsman, so I don't really need to know, oh, it's 56, no, it's 57. So this is not that important to me. So that was easy. Digital stuff, always easy. Tracking temperature, and yeah, this is not really the device you want to use when running. So, and also this one is, yeah, it looks strange. That was an external sensor. And the reason for that was, I thought, okay, to make it smaller, let's take an external sensor. Great idea. So, but you can imagine, you have this cable and you have to tape it somewhere. And so I ordered some stuff for for the hospitals where they do the EEG thing, where they also tape cables and sensors on your skin. So I ordered that to tape it here somewhere to get a good temperature. Terrible. It's totally terrible. If you start running, then it falls down, and you have the cable, and so this is not really good. From the pure results from measurement, it's all the same. That doesn't really make a big difference. But the handling and the size, that was the difference. So here, this is a digital one. This is the TMP36. But if you would like to run it with a Pi, you need a DA converter. So this is, again, it was too big for the case. And then I stumbled upon this little guy, which is really, really small. And it's a BMP180. It uses I2C. And that's really small and has also a pressure sensor. And most important is that the power consumption is really, really low. And that's the most important thing when building a wearable. Then battery is crucial. So you need your battery, and it should last as long as possible. So I use this one, and I don't show you the code because there's even an example. If you go to the Pi4j page, there you see an example how to access a BMP180. It's not really rocket science. That's easy. That's with the whole thing. Java was not the problem, building this thing. That was easy. That was really coding. You just see, oh, I need that. Okay, code it, done, works. No problem. The problem was make it small and make it reliable. That was the real problem. And have some strategies, for example, like if it's not in use, if the position doesn't change, then don't do the updates. And if you recognize, oh, it's moving, then start updating and all that. That was the bigger problem. So when we came to the haptic feedback, I found this little guy with this little LilyPad vibe. And this is just a little motor. And you can start or stop it just by getting power to it or take the power away. So this is very easy. And again, what I do is I take the GPIO. This time I take a digital pin output. And the only thing you have to do, this is just an example, you just switch the pin on, and after a certain time you switch it off. What you can do with this kind of things is, and the only reason I built that was on my Android phone, there is something like you can create your own vibration themes. So I thought, oh, that's nice. I can do that in code. So that means if the battery is running low, this thing will do SOS. So, and you can recognize, oh, what's that? Oh, I know that. Oh, battery is running low. So this is really something you can learn. It's not hard. The bigger problem was because it's vibrating and the GPS sensor is very sensitive to vibration. It's not a good idea to put that close to the GPS sensor. So I had to put it here somewhere and then try to separate it so that it's not, the vibration is not too hard to the GPS sensor. And this is all the problems. But you see the code is a piece of cake. For programmers, that's not really a big deal. That was a good one. Did someone ever try text-to-speech on Linux? The open source stuff? Or there's even a Java stuff. Did someone try that one? That's terrible. It sounds like 1970s something. It's like really, you think, what? Sounds like that? Oh, no, terrible. So, and if you use something like this, if you run on the street, cars going by, it doesn't really work. So I thought, first of all, what can I do? What would be interesting? So the device will tell me every minute the heart rate. This is just as an indication. You say, oh, okay, now it's like this, it's too high, it's not. as a runner, you know that kind of stuff. Then, because I know the position of the runner, I contact the weather service and get the weather information for that location. And if there's a weather warning, then I will send a message to the runner, and then it will say something like, 5 kilometers ahead, northwest, there will be some thunderstorms or something like that. So you can get things like that. That was easy. And of course, we talk about ultra marathon, means more than 42 kilometers. So in this case, sometimes you have a team along the track. How can the runner know where someone is? And how can the people along the track know where the runner is? Right? So I built something that if the runner, because it updates his position, so I put something on the server where it knows, using MQTT, where the team members are. And the team members get push notifications and say, oh, the runner is coming 500 meters from that direction. And the runner will get some information, oh, there's this guy standing in whatever, 600 meters in that direction. And the direction we can get from the running, so if he's running in that direction, he knows, okay, this is north, for example, then this is, for example, east, west, whatever. So we can do that. And if I'm, for example, monitor the runner from my home place, having a desktop application I will show to you later, I can type in like a short message on the phone, and then it will send it to the runner and it will read it to the runner. So I can do something like, and we did that during a session in Munich. We had a real runner outside, and then we said, okay, because we know where he is, take the next street on the right. And then we saw on the map, oh, now he's moving right. So that it works. So that was really fun. And this is the most important thing is we have I have a high quality voice from a company called Cepstral or Capstral. And this is the link. Because you won't find it on the website, they ported one voice to the Raspberry Pi. And this is really high quality. It's 29 euros the voice, but it's worth. And it's lucky you, it's a British voice. So because they have voices for all the different languages, but only one was ported, and this is a British one. And it sounds quite good. So, and this is also available for desktop. So if you ever need text-to-speech on a desktop computer, that's the way to go. And this is all you need. Not much code, right? Because they come with their own little shells command, which is called Swift. And the only thing that it takes is the message. And I run it on the command line via exec, and then it talks. And it just, on the Pi, it takes maybe a second to convert the text to speech. It's a second, sometimes 2 seconds. So, but this is not really important because time is not the problem here. But it was interesting that it works quite good. So connectivity is the next point, and this is really heavy lifting. This is the most important thing when doing a wearable stuff, is that you would like to get the data somewhere live. First approach that I did was Wi-Fi. Simply using a phone and a little USB adapter like this. And the good thing is that you just open a Wi-Fi hotspot with your mobile phone, and then you can use the high data rate from the phone, and all the heavy lifting with the internet connection is done by the phone. The problem is your device then definitely needs a battery, and the power consumption of Wi-Fi is really high. And if you imagine you have the wearable here in one pocket and the phone in the other, and then you have a Wi-Fi network for that. It doesn't really make sense. It works very easily, but it's not really, that's not the way to go. I also built a version that was totally autonomous with its own 3G modem, and then you need 2 batteries because the modem alone it sucks the battery like, I don't know. So you can have a battery life of about maybe 2 hours if you are lucky with a huge battery. This thing now runs for 7 to 8 hours on one battery charging, which is great. But then I thought, wait a minute, what does all the other companies, what do they do? And they use Bluetooth. So, okay, just exchange this guy with this little USB thing, and this is a really tiny one. So put it in, and then you can use Bluetooth, and you can use Bluetooth tethering. And that works quite good from Linux because you can use PPP. It's not the newest protocol, but it works. So the only thing that you need, you have to set it up, you have to combine the phone with the wearable ones, and then you have to set it up in Linux, which is really just a couple of shell commands and configurations. And after that, you can directly call from Java some URL, and it will automatically use the PPP protocol to connect to the phone and then use the phone connection. The data rate is limited, that I have to say, but it's more than enough for the stuff that I do. Which leads me to communication in principle. So I use MQTT. Does someone know MQTT? Yeah, this is a really nice protocol. Message queue telemetry transport was invented by IBM, and it's publish and subscribe model. And in principle, it works like this. If we have the runner on one side and the clients, whatever it is, on the other, then we have a message broker. And in this case, I really just use Mosquito, which is a 76 kilobyte C program that comes with Linux. If you have a Raspberry Pi, you can just do apt-get install Mosquito, and then it will install it. And you define some topics, like in this case, JRunner and JRunner/message. And then if the JRunner sends a message to that topic, then all clients that are subscribed to that will directly be informed about the new message. And if the client sent a message to this other topic, then the runner. So I do the communication between the wearable and the clients. And so the setup looks like this. So I have my wearable talks via Bluetooth with the phone. Then we use the cellular connection, and this goes to my broker, the Mosquito, which is running again on a little device, which is an embedded device, also from hard kernel. And every message that arrives here, and this is the nice thing, I can subscribe with as many clients as I like, as long as the broker can handle it. But for this, it's the Mosquito is really good enough. I think it's good enough up to, I'm not sure, 40,000 connections. I might be wrong. It's not really good for enterprise stuff, but for all the stuff that you do in your private things, it's perfect. So I started with desktop. I just added a mobile client. I added a smartwatch client. I added a database server client. So that was very easy, and all get the same messages, and so you can write little programs for all these different devices. So MQTT is a very lightweight binary protocol, so you don't have all the overhead with XML and that stuff, which is great. And it was made for low power consumption and really bad networks, which is also very good for wearables. It has support for so-called quality of service, so that means different stages of making sure that the message really reaches the target. This is possible. We have 3 different ones in MQTT. It's a perfect fit for machine-to-machine communication. And there is a Java library. Eclipse Paho is the project, and there is also C++, Python, and other stuff from Paho. But the Java library is not the newest one, but it works quite well. So the final setup was like this. So this is the old GPS receiver, but you see there are a lot of wires, and if you have to solder them and put them in the case, that leads to different problems. So I ended up with creating my own PCB, and then you don't have to put all the wires in because you have the wires hard-coded on the PCB, which gives you more space. And this is how it looks like when it's open. Here you see the PCB thing, so I etched it by myself, designed it by myself, and all that stuff. It's not that hard. I did that before, so it's really easy to do. And yeah, you see the wires. And the vibration motor, it's covered with some... it's some sticky tape that has some foam outside so that it doesn't give the vibration to the outside, just to the case. And I have a 1200 milliamps lithium polymer battery. Like I said, it runs 7 hours continuously, sending every 5 seconds, which is good. And this is in principle the setup, and I use it like this. It's some kind of like a holster, which is made for runners, and it's about, I don't know, 30 euros or something. And you have the mobile phone on one pocket and the device on the other. And you have also an audio out here on one side where you can plug in the headphones. And you have this polar strap that you can put around your body. That's all it needs, and we tested it with the runners. And they said, yeah, it works. It's not too heavy, so you can run even a marathon with that. It's no problem. The phone... it's the bigger problem because it's really big. It gets warm because of this sending the messages, and it depends on the network quality, but this is always the same. If you use a mobile phone somewhere in Alaska, might not be a good idea if there is no network connection, so the whole thing doesn't work. But if you run in cities or close to cities, then that works quite well. To remote control it, I told you already, I created a mobile app. That's what it looks like on a watch. This is on a smartwatch, and this is written in JavaFX. So I just wrote one time, I've wrote the program, and I compiled it for Android, for iOS, and also for desktop, which is possible if you use JavaFX ports, which is a community project, which makes it possible to port a JavaFX application to all the different platforms. So you have battery time, distance, duration. We have the current beats per minute. We have a little indicator, which is a heart, changes the color. If you push this little button, then it will show you a static map just to give you an overview. Where am I at the moment? And if you swipe down, you will see that menu where you can push an alert button, which sends an alert message. For example, you broke your leg or whatever it happened. So you can mark a spot. If you say, oh, that's very interesting here, mark it. You can stop the recording of the track, and you can reset the track, and also switch off the whole device is done here. Because I can switch it on with this button, but I can't switch it off. That's the problem. I can, but then it's the hard switch off, and then the SD card is gone. And this is just for exit. And the same code, and it's really, believe me, this is really the exact same code. I just compile it for different platforms. I don't change anything. So it's like it's used some kind of a responsive UI approach where I just recognize the size and the orientation of the screen and then arrange the UI. So that means that's the reason why here we see the 0 at this position, and here the heart is on the right side because it's just smaller. But that makes it very convenient to code. And on the desktop side, this is my monitoring app. And you see there's a lot of icons around it with all the different things that I can monitor. It has the map. It uses OpenStreetMap. This is the location. You will see the start and end points in different colors. You will see the points of interest. You can see teammates that use the little software called OwnTracks. And this is OwnTracks is using MQTT and do something like Latitude from Google did before. And they do the same. But if you have your own broker, you can set up your own group of friends, and then you can share the location. And I use that tool. And as long as someone is logged in, they will show up here, the teammates. And then you can see, okay, this is that guy. You can also click on the icons, and it will show where the teammates are on the map. And then we have charts where you can see this is the altitude and this is the heart rate, colored with different heart rate zones, because there are fitness zones and aerobic zones and stuff like that. So you can see that. You can save tracks and reload tracks from a calendar and from a database. Everything is stored in MongoDB. And that's it. So usually the session will go for 2.5 hours. I have 140 slides. I really stripped it down to the at least possible version. If you have any questions, I would like to ask you, send them to me. You can tweet me. I will answer them. But I really have to leave now. Otherwise, I won't get back home. And I have to go to Brazil tomorrow. So this is my main problem. Thanks for your attention.